Welcome, everyone. Today, we're embarking on an exploration into the fascinating world of programming quantum computers.
Indeed. We're drawing insights from a key technical resource focused on essential algorithms and code samples.
Our aim is to demystify how these new machines work, what makes them uniquely powerful, and how you, as a programmer, can start to interact with them.
This overview is generated by AI, designed to help you quickly grasp the key information.
We'll navigate through the foundational concepts, from the smallest unit of quantum information, the qubit, all the way to, well, mind-bending applications like quantum teleportation.
That's correct. Our goal is to provide a clear, practical understanding of these concepts. We would focus on the logical behaviors and real-world applications.
And we'll be carefully avoiding deep dives into complex quantum physics or advanced mathematics, keeping the language as straightforward as possible.
Think of this as your guide to becoming well-informed about the practical side of quantum programming.
Okay, so let's begin by setting the stage. The first section of our source material highlights that quantum computers are no longer just a theoretical concept. They are a tangible reality now.
Exactly. And what's particularly insightful here is the idea that the true potential of any new technology is only fully unlocked when practical-minded experts begin to experiment with it.
And this book is specifically designed for programmers. So what does this mean for someone looking to get into quantum coding?
It means this resource is a direct, hands-on guide. It doesn't dwell too much on the underlying physics.
Right.
Instead, it offers practical examples and code. You'll find code primarily in JavaScript for the QCEngine, which is an online simulator, as well as Python and QASM.
So it really emphasizes learning by doing.
Precisely. For background, you only need basic programming knowledge, some simple math like functions and binary numbers, and maybe a very elementary grasp of algorithm complexity. Big O notation.
No advanced calculus or quantum theory required then.
No, not necessary to get started with this material.
What's a critical distinction the book makes early on about how these quantum machines fit into our existing computing landscape?
A key point is that a quantum computer is better understood as a QPU, a quantum processing unit.
Okay.
And it acts as a co-processor. It's not designed to replace all current computers, but rather to expand the range of problems we can solve.
So maybe something like a GPU, a graphics processing unit in a classical system.
That's a very good analogy. Your normal CPU still handles most of the program, sending only specialized, computationally intensive tasks to the QPU.
That perspective integrates quantum computing into familiar computing structures, which probably makes it less alien for software engineers.
Exactly. The QCEngine simulator is also introduced as a crucial learning tool here.
Like the one that runs in the browser.
That's the one. It lets you run code samples right there without any installation, and it uses a clear circle notation for visualizing qubits.
And is it effective?
Yes, this simulator is fast and highly effective for learning, even as the real QPUs continue to develop.
That makes a lot of sense, framing it as an extension rather than a replacement. What kind of tools and instructions does this book offer for hands-on learning? And what are the current practical limitations we should be aware of?
Well, the book provides code samples that are compatible both with cloud-accessed prototype QPUs, such as those offered by IBM, and with various simulators.
The practical experience is always within reach.
Correct. It also introduces the core QPU instructions, things like CNOT, CNOT, had, phase, read, write, and swap. These are the fundamental operations you'll use to build quantum programs.
And the limitations.
Regarding limitations, while simulators are currently restricted to around 26 qubits, and while real hardware can have up to 70 physical qubits, they often lack robust error correction. The book cleverly navigates this by focusing on logical qubits. These are abstract, error-corrected qubits, allowing programmers to focus on the logic without getting bogged down by current hardware complexities.
So the comparison between a QPU and a GPU, both acting as co-processors and perhaps presenting similar debugging challenges, offers a comforting familiarity for software engineers.
It does seem that way. It provides a thoughtful way to ease into a new paradigm.
And how is the material itself structured to facilitate this learning journey?
The book is divided into 4 progressive parts. It starts with programming for a QPU, then moves to QPU primitives, then QPU applications, and finally into the future.
So it's designed to incrementally build your intuition and practical skills.
Exactly. Moving from basic operations to complex algorithms and future possibilities.
With that overview, let's shift our focus to the very heart of quantum information, the qubit. What exactly is a qubit? And how does its behavior open up new possibilities compared to a classical bit?
Okay, the qubit. It's the basic unit of quantum information. Now, like a conventional bit, when you measure a qubit, you will always observe either a 0 or 1.
Always 0, 1 upon measurement. Got it.
However, before measurement, a qubit can exist in what's called a superposition of states.
And that's not just a 50-50 chance like a coin toss.
No, it's more subtle. It represents an infinite spectrum of possibilities for its state before you observe it. This state is visualized using circle notation.
Tell us about that notation.
So a shaded area in one circle shows the probability of getting 0, and in another, the probability of getting 1 upon measurement. The relative phase is also crucial.
Phase.
Yes, represented by the rotation of the one circle compared to the 0 circle. Only this relative rotation matters, not the absolute orientation.
That's a fascinating concept. So much information hidden before we even look. What are the fundamental operations we can perform on just a single qubit?
We have several key operations. The NOT gate simply flicks the state, turning 0 to 1 and 1 to 0, and it works even when the qubit is in superposition. This operation is reversible.
Okay, like a classical NOT.
Similar, but quantum. Then there's the HAD, or Hadamard operation, which is really unique to quantum computing. If you apply HAD to a qubit initially in a 0 or 1 state, it creates an equal superposition, meaning both 0 and 1 outcomes are equally likely upon measurement. HAD is also reversible.
Interesting. What else?
The read operation. This is where measurement occurs. It collapses the superposition, giving you either a 0 or a 1 based on its probabilities.
And this destroys the quantum information.
Correct. It irreversibly destroys the information contained within the superposition. Finally, write allows you to set a qubit to a definite 0 or 1 state. This is also an irreversible action.
Can these basic operations, even just on a single qubit, enable us to do something fundamentally different from what a classical computer can achieve?
Absolutely. A compelling example is generating a perfectly random bit.
How does that work?
By starting a qubit in the 0 state, applying a HAD operation to put in that equal superposition, and then performing a read, you obtain a truly unpredictable 0 or 1.
Ah, the basis for a quantum random number generator, or QRNG.
Precisely. While simulators use pseudo-random numbers, a real QPU produces genuinely unpredictable results. And you can scale this up to generate random bytes by doing the same thing on multiple qubits simultaneously.
Let's delve deeper into the phase operation you mentioned. How does that contribute to controlling a qubit state?
The phase operation is subtle but powerful. It changes the relative phase of a qubit by a specified angle. Essentially, it rotates the 1 circle in our notation relative to the 0 circle. This operation is fully reversible.
And what does that allow?
By using phase, we can create other important quantum states beyond simple 0 and 1 superpositions, states often labeled like plus or man-y.
Correct.
The book underscores a crucial point here. The full power of a quantum computer truly emerges when you combine HAD, phase, and crucially, multi-qubit gates. Not just by using HAD alone.
You've described what quantum computers can do. Is there anything fundamental they cannot do? Something we maybe take for granted in classical computing, like making a simple copy?
That's a very important question. And it brings us to a rather mind-bending insight. Quantum information cannot be copied if you don't know what it is.
Cannot be copied.
Correct. It's a principle called the no-cloning theorem. This isn't just a quirky physics fact, it's actually a foundational pillar for things like quantum security, because it makes eavesdropping detectable.
So it forces a complete rethink of how we manage digital data.
In a quantum context, yes. You can only make multiple copies of a known quantum state by preparing them repeatedly. While it might seem like an inconvenience at first, this unique property opens up entirely new computational possibilities.
That's a profound difference from classical computing. Given these basic operations and the no-cloning theorem, can we combine them in interesting ways to create new kinds of gates or achieve novel computations?
Indeed. For instance, a classical NOT gate can actually be constructed by combining 2 HAD operations and a phase 180 operation.
Okay, building familiar gates from quantum ones?
But even more intriguingly, we can create something like a root of NOT gate, or RNOT. This is a gate that, when you apply it twice, performs the equivalent of a single NOT operation.
Apply it twice for one NOT.
Exactly. It demonstrates how carefully manipulating the relative phase allows for entirely new computational behaviors, really stretching our understanding of logic gates.
What's a practical application that truly showcases the power of phase manipulation and these unique properties of qubits?
The concept of quantum spy hunter illustrates this quite beautifully. It's essentially a simplified version of quantum key distribution, or QKD.
How does that work?
Imagine Alice and Bob wanting to send a secret key using qubits. If a spy tries to intercept and read the qubit, they have about a 25% chance of being detected.
Why?
Because reading a qubit, as we said, collapses its superposition, irreversibly altering its state. So the spy leaves a trace. This inherent property of quantum mechanics makes truly secure communication possible, demonstrating the practical implications of phase manipulation and measurement.
Transitioning from single qubits, let's explore what happens when we bring multiple qubits together. Chapter 3 introduces quantum entanglement as a powerful new phenomenon. How do we visualize and begin to work with systems involving more than one qubit?
Okay, multiple qubits. For n qubits, our circle notation expands. We now need 2 n circles, with each circle representing a possible n-bit value.
So for 2 qubits, that's 4 circles. For 0, 0, 1, 10, 11.
Correct. Circles for the values 0, 1, 2, and 3. Each circle continues to show the magnitude and relative phase for that specific 2n state. Now, while some multi-qubit states can still be described by the individual states of each qubit,
like just putting 2 independent qubits next to each other.
Essentially, yes, but others cannot. Consider an equal superposition of 0, 0, and 111 for 3 qubits. Here, the individual qubits are linked.
Linked how?
In such a way that their measurement outcomes are always perfectly correlated. If one is measured as 0, they all are 0. If one is measured as 1, they all are 1. This deep, non-classical connection where qubits cannot be described independently. That's what we call entanglement.
So entanglement is this unique quantum link that binds qubits together. How do the single qubit operations we discussed earlier, like NOT, had, and phase, function within such a multi-qubit system?
Good question. These single qubit operations still apply, but they act on what we call operator pairs.
Operator pairs.
For any specific qubit, its operator pairs are the set of circles whose values differ only by that qubit's bit value. For instance, applying a NOT gate to the second qubit in a 3-qubit system would swap the states between circle pairs like 0, 0, 0, 2 and 0, 0, and between 1, 0, 0, 1 and 3, 0, 11, and so on.
I see. And what about reading a single qubit?
It's also important to remember that reading just a single qubit in a multi-qubit register will collapse the entire multi-qubit state. It eliminates all possibilities inconsistent with the measured value across all the circles.
This sounds like where the true computational power begins to emerge. What are multi-qubit operations and how do they directly create this entanglement we've been talking about?
The CNOT, or controlled NOT gate, is a foundational multi-qubit operation. It applies a NOT operation to a designated target qubit only if a specified control qubit has the value 1.
Conditional logic, basically.
Exactly. And critically, if the control qubit itself is in a superposition, applying CNOT will create an entangled state.
Can you give an example?
Sure. If you start with 2 qubits, both at 0, apply hadid to the first qubit to put it in superposition, and then use that first qubit as a control for a CNOT on the second. You create a superposition of 0, 0, and 11.
The state where they're both 0 or both 1.
That's right. This is known as a Bell pair. If you then measure these qubits, they will either both be 0 or both be 1, each with 50% probability. It demonstrates a correlation impossible to explain classically.
Are there other important multi-qubit gates?
Yes. Another important one is CPHASE, which conditionally rotates the relative phase of a target qubit when a control qubit is 1. A CZ gate is just a specific CPHASE with a 180-degree rotation.
That's a subtle but powerful effect. Tell us about phase kickback. What is that? And why is it considered a useful trick in quantum algorithms?
Phase kickback is a particularly clever and powerful effect. It's where applying a conditional phase rotation to one set of qubits based on the state of another set can actually cause phase changes to kick back onto the first set.
Kickback?
Yes. Essentially, you can use one register to imprint specific phase rotations onto terms in another register through these conditional operations. It's an indirect way to manipulate quantum states and a very valuable technique in designing many quantum algorithms.
So if we can build these conditional operations, does that mean we can construct almost any complex conditional logic we might need?
Precisely. You can indeed construct virtually any conditional operation, even if a specific QPU doesn't offer a particular conditional gate, like, say, a conditional Hadamard.
You can build it.
You can often synthesize it from existing gates like CNOT, CZ, and phase. For example, the book shows how a CPHASE can be built using 2 CNOTs and 3 phase operations.
What about more complex gates?
Another crucial gate is the CCN, or Toffoli gate. This is basically a CNA, but with 2 control qubits. The NOT is only applied if both control qubits are in the one state. This is vital for implementing classical logic gates within a quantum circuit.
And swapping qubits.
Ah yes, the swap gate, which exchanges the states of 2 qubits. This can be a fundamental hardware operation, or it can be built from 3 CNAs. And naturally, there's a C-swap, or controlled swap, which conditionally exchanges 2 qubits based on a control qubit.
Another intriguing concept I came across is the swap test. What problem does this solve, and why is it so important for quantum computing?
The swap test is incredibly ingenious. Its purpose is to determine if 2 qubit registers are in the same quantum state, but without actually reading out their individual states.
Because reading them would destroy the information.
Exactly. It avoids collapsing the states. It works by using an extra qubit, an auxiliary qubit. You apply a Hadamard gate to this auxiliary qubit, then a controlled swap operation using it as the control, and finally another Hadamard.
And what does that tell you?
If, after the sequence, the auxiliary qubit reads 1, it tells you the 2 input states were identical. If it reads 0, they were different.
That's clear.
And what's more, the probability of measuring 1 is directly related to the fidelity or similarity between the 2 input states. By repeating this test, you can estimate this probability, providing a way to verify quantum algorithms and compare states without collapsing them.
So what's a practical application that really drives home the power of entanglement and these multi-qubit operations?
The concept of remote-controlled randomness provides a great example. This program uses entanglement to link 2 qubits.
How does that work?
It links them in such a way that measuring one instantly influences the probabilities of the other, even if they are physically separated. For instance, if qubit A is measured as 0, maybe qubit B then has only a 15% chance of being 1. But if A is measured as 1, maybe B now has an 85% chance of being 1.
So it demonstrates these non-local correlations.
Exactly. It shows that while entanglement doesn't transmit predetermined information faster than light, it fundamentally links these quantum states in a way that classical systems just cannot replicate.
Let's move on to Chapter 4, Quantum Teleportation. Now, this sounds like something straight out of science fiction. How can we actually teleport something in the quantum world?
Quantum teleportation is, well, it's precisely what it sounds like in a way. It transports the exact quantum state that means its magnitudes and relative phases of one qubit to another.
The exact state.
Yes, but the original qubit is destroyed in the process. It's a perfect transfer of quantum information, not a copy. The source material notes this has been physically achieved over various distances, from millimeters up to potentially interstellar scales.
How does the process work?
It involves 3 qubits. Alice has her payload qubit, the one whose state she wants to teleport, and then there's an entangled pair of qubits, one held by Alice, one by Bob, who might be far away.
Okay, 3 qubits.
Alice performs operations that entangle her payload qubit with her half of the shared pair. Then she measures her 2 qubits, the payload, and her half of the pair. This gives her 2 classical bits of information.
Regular bits, Seelys and ones.
Yes, classical bits. She sends these 2 bits to Bob through any normal communication channel. Based on which 2 bits he receives, Bob performs specific single qubit operations on his half of the entangled pair.
And that does it.
Remarkably, yes. Bob's qubit is transformed into the exact original state of Alice's payload qubit.
That is truly incredible. How does this translate into actual programming? What does the code for such a process look like?
The example provided in the book uses QASM, quantum assembly language, which is suitable for real QPUs like IBM's. The steps are quite defined.
What are they?
First, you create an entangled pair. Alice and Bob establish a Bell pair using Hadamard and CNOT gates. Second, Alice prepares her payload qubit. This could be any specific quantum state she wants to send. Third, Alice sends.
How does she send?
She links her payload qubit with her entangled qubit using CNOT and HAD operations. Then she performs read operations on both her qubits. This yields those 2 classical bits. Fourth, Bob receives. Alice sends the classical bits to Bob. Bob uses these 2 bits to apply specific X and Z operations, basically NOT and CPHASE 180 type operations to his entangled qubit.
And that transforms his qubit.
Correct. It becomes Alice's original payload state. Finally, you might want to verify success. Bob could try to reverse Alice's preparation steps on his qubit. If it reliably returns to a simple 0 state, teleportation was successful. Usually, you need to repeat the whole process multiple times to build confidence.
That's a profound sequence of events. The book also discusses gate teleportation and teleporting entanglement. How do these advanced forms of teleportation work, and what do they enable?
Right. Gate teleportation is where you can effectively apply a quantum gate remotely. Imagine Alice needs to apply a specific gate, but her local QPU doesn't have it. She can teleport her qubit state to Bob, who does have the gate. Bob applies the gate to his qubit, which now holds Alice's state, and then he can teleport the qubit's modified state back to Alice.
So like quantum computing in the cloud?
Exactly. It allows users with limited capabilities to leverage remote, more powerful QPUs. Then there's teleporting entanglement, also known as entanglement swapping.
What does that do?
This allows Alice and Bob, even if they are far apart, to create entanglement between their computational qubits. They do this by using a pre-shared entangled pair between them and only performing local operations on their ends. It's a fundamental building block for larger quantum networks.
This sounds like teleportation is far more than just a party trick. What's the broader significance for the use and development of quantum computing?
Teleportation isn't merely about moving quantum states around, although that's useful. It's actually a fundamental operational tool within quantum computing itself.
Also,
it enables the precise shuttling of quantum information where needed. It also offers a way to work around the no-cloning theorem when dealing with unknown states. Entangled pairs essentially become a kind of consumable resource in these operations.
so many algorithms rely on this.
Yes, many multi-qubit operations and complex quantum algorithms implicitly rely on the principles behind teleportation to form sophisticated entanglement networks and perform their computations. It's really an essential part of the quantum toolkit.
What an incredible journey through the world of quantum programming. We've covered the basics of qubits, how they behave in superposition, the essential operations, the unique power of entanglement, and even the astonishing reality of quantum teleportation.
It's truly foundational. The ability to manipulate superposition and entanglement using tools like circle notation and understanding operations like HADE, CNOT, and phase. This is critical for anyone looking to truly grasp this evolving field.
These practical insights into programming QPUs seem invaluable for software developers wanting to get involved.
I believe so. It helps bridge the gap between classical thinking and the quantum approach.
And if you're interested in diving deeper and experiencing these concepts firsthand, we highly recommend reading the book that provided these amazing insights. Programming Quantum Computers: Essential Algorithms and Code Samples.
It really does offer practical, hands-on examples that you can run in simulators or even on actual quantum hardware. It makes it an excellent resource for practical learning.
As we conclude this session, maybe consider this thought. If the fundamental laws of physics allow for information to be teleported and computation to be remotely applied through entanglement, what entirely new forms of secure communication and distributed computing might still be waiting for us to discover as we continue to push the boundaries of quantum technology?
A fascinating question to ponder.
Thank you for joining us on this exploration. We hope this has given you a clear understanding of the fascinating world of quantum computing.